Good afternoon, everyone. Welcome to the ITS weekly seminar. Today, we're delighted to have Professor Kaan Ozbay as our speaker. Professor Ozbay is with the Civil and Urban Engineering Department at NYU Tandon School of Engineering and also with the Center for Urban Science and Progress. He's the director of the C2 Smart USDOT Tier 1 Center. He taught at Rutgers University for many years before joining NYU. His research spans a wide range of transportation topics, ranging from data analytics for advanced technology and sensing applications in smart cities, development of simulation models of large-scale complex transportation systems, to application of operation research techniques in network optimization and humanitarian inventory control. Professor Ozbay published extensively in professional journals, and he has also published 4 books. He received several Best Paper Awards and also the National Science Foundation Career Award and the IBM Faculty Award. With that, I would like to welcome Professor Ozbay to give us the seminar. And before he starts, I want to remind our student audience that if you have a clarification question, you can submit it through chat. Otherwise, we'll leave all the questions to the Q&A. And during the Q&A, you can use the raise hand feature to ask your questions, or you can type in the question in Q&A. And also for our outside audience, you can use the Q&A feature to ask your questions. Okay, with that, I'll give the Zoom room to Professor Kaan Ozbay. Kaan?
Hey, thank you, Michael, and thank you, everyone. And Michael, thank you for doing a great job summarizing my bio. It was great. Thank you for all the students attending the webinar. For us, this week is the finals week. I don't know if it is the same for you guys. So I hope that you'll have patience to listen to me. I'll try to make it as fun as possible. And again, feel free to ask me questions. So today I'm going to talk about, major disruptions. So what a title: earthquakes, hurricanes, pandemics. Sounds like our time, all these things are happening. So I'm just going to try to give you just the research side of it, not the bad news, but good news, and hope you'll get some ideas. Okay. So the outline, I'll just give a very brief introduction about C2 Smart, our center, then talk about this whole idea of a city as a lab and big data, which is what we do, and then talk about evacuation modeling and calibration with some focus areas in terms of capacity loss and evacuation zone modeling. I will skip the resilience part of it because it's too much, and then I'll wrap up with some conclusions and future work. The center, the C2 Smart, unlike your center, it's a relatively new center. It was established in 2017 as part of a consortium of 5 universities. So there's Rutgers University, where I was before. There's City College of New York, University of Texas El Paso, and University of Washington. And the whole idea of our center is to use the cities of different size as a place to do research. So this is not new, but it's becoming more interesting with the idea of smart cities, which I will talk a little bit more in a minute. So we kind of would like to claim that we are talking about cities as living laboratories, and then we depend on not only on researchers, but also agencies and stakeholders to work with us. And I think there's a lot of success in that sense, what we have done. Why this is happening? This is happening because there are a lot of new ways of getting data, sensors, smartphones, and big data, and also connected autonomous vehicles. So that really, I mean, sets the stage for this whole idea of city as a lab. I'm going to quickly go through this slide because most of you are not interested in this most probably, but the main idea is when we did the competition, we focused on the US DOT's vision of a smart city and then looked at different research areas of urban mobility, urban analytics, and resilient and smart transportation infrastructure. So we're not doing everything, unlike some of the big centers. We are focusing on big data, analytics in a city environment. Okay, so I mentioned this. So these are our core research areas: connected and autonomous vehicles, infrastructure sensors, big data analytics, and micro transit, micro mobility, and mobility as a service. And then we kind of claim that we can combine all of this research within the framework of cyber physical testbeds. So there's simulation testbeds, but there are also physical testbeds. And I'm not going to go into details of this today, but our idea is to converge these different kinds of testbeds together. So for example, we have, if there's anybody from New York, Brooklyn Queens Expressway, and it's kind of in dire needs for renovation. So we are actually installing sensors, cameras, a small section of it, which is due for renovation, reconstruction, to understand the condition of that highway section. And then we are combining that with a traffic simulation and transportation simulation model that we built, so that there is this back and forth between simulation and the infrastructure. So that really covers, for example, the infrastructure sensors and resiliency, big data analytics, and also we are part of the connected vehicle pilot test that New York City DOT is doing, which is a very large, one of the largest connected vehicle test beds with like more than 3,000 vehicles. And then we are hoping that we'll be able to get data from that pilot test and then try to combine everything together under one umbrella. So let me just talk now, come back to my main topic. What is the future of cities and mobility in the era of major disruptions? And most of you now are tuned to this due to COVID-19 because we really felt, unlike any time, the effect of that. When there's a hurricane, when there is a flood, when there is an earthquake, it's limited in location. It's only one area. But with COVID, actually, the whole world felt that. So I think it's a nice question, right question to ask. What is the future of mobility / transportation in the aftermath of COVID-19 pandemic, and also in understanding that there might be more of these disruptions due to global warming and so on, like hurricanes and other not so nice events. So I kind of was thinking about this, and I said, I kind of thought about this, and this is the finals week. So it's like a small anecdote, like Dr. Einstein was giving, and I'm sitting in Princeton, like probably 5 minutes from his office, and the student was giving the exam, and then he kind of figures out that it's the same question as the last year's exam. So this is the fear of all professors, like, what did I do? And then the student gets panicky, and then he's asked the question, then Einstein says, yeah, true, but this year the answers are different. So this is really the same idea for mobility and transportation. There's not one answer. There's not one way of doing things. The questions are always pretty much the same, but how can we really adapt to what's happening? So that's kind of probably summarizes with what I have in mind for this talk. So city as a lab, really something that we've been working probably in the last 10 years. And the key here is really sensors and sensing. And on top of it, there's a lot of new things are happening, basically big data, artificial intelligence. So we know how to deal with the data. But more importantly, now we want to move to a world where we don't just get this data offline and do the data analytics offline, but do closed loop decision making. So we want to just move away from the open loop decision making that takes sometimes months and years. And actually, you've seen the importance of that with COVID-19. There was no time to wait. So you had to make decisions and then see the results of decisions in the cities in terms of transportation system, frequency of transit, and so on, and then change your decisions based on the response you're getting. Of course, the ultimate idea is to have an autonomous city in terms of certain services that you could really let the city respond to what happens. It's by no means means that we should get rid of the human beings, decision makers, but it's something that will help them to make these decisions. So there's always going to be a human in the loop, I guess. So this is like some of the data. I'm going to flash some of these very quickly that we collect in terms of transportation. Most of you are using one or two of these categories, but really the idea is not only to have this data collected, but have this data collected almost in real time, online, and make it accessible to users, and also have them in one place. So as C2 Smart, we've been collecting, obviously, some of the data that all traffic engineers are familiar with: loop detectors, closed circuit TV, Bluetooth, toll transactions. But more and more, we're collecting smartphone data, Twitter data, social media data. And then, again, the idea is not just to use these data sets in isolation, but use them together. How do we do that? So we are building something we call Urban Data Observatory, basically to bring all this data together in a very large database or computer, and then make sure that we use that data for different research and experiments and so on. Also make it available to different kinds of end users, not just researchers, but also agencies, public, and so on. So this is something that we've been working for the last couple of years with some success. Now we're working with the New York State to do some portions of that. I think this is going to be kind of game changer in the sense of accessing very large amounts of data very easily. Here I have, I think I coined that, there's a data black hole problem. So you bring all this data and people, if they start trying to transfer that data out of the server, it's not good. So we're also trying to build apps on top of the data server so that you don't have to really move data from one computer to another. You can do everything on the server. So this is kind of a depiction of what we're trying to do. And then this is work in progress. So now let me just talk about these extreme events and what we mean by them and the type of research that we do. So there is an operational side of it. That means you are trying to manage the emergency evacuation operations, and it can be unplanned events from very simple like traffic accidents, but not like everyday accidents only. It can be big accidents like hazmat and so on, big weather events or infrastructure failures, let's say bridge failure, or planned special events like a big final, Champions League final, the ones who are following the European soccer, this is a big thing, can be big political conventions or something like COVID-19. All of a sudden, many things in terms of transportation in New York City changed because of COVID-19, and you need to make sure that you manage the operations. You can also look at it from the planning and management perspective, especially for advanced notice events like hurricanes. In this case, pandemics, I mean, you cannot really predict them years before they happen, but you have a few months to plan. And there are some non-notice events like earthquakes. So we are, as I said, building a kind of a framework for physical environment, natural environment models, and then agent-based simulations to deal with this kind of problems. So the cyber-physical testbed that we are building has different components. So there's a big, very large MATSim simulation. So for those of you who are not familiar with MATSim, it's an activity-based multi-agent simulation for passenger travel, and now we're adding freight on top of it. We also have a Sumo model, traffic model of certain parts of the city, New York City, and then we are trying to integrate these two. So MATSim is agent-based, but the traffic model is not very detailed. Sumo is a traffic model, but doesn't have many capabilities of MATSim. So we're trying to incorporate the two. And actually, our other partner, University of Washington, Seattle, they're also trying to do something very similar to that. And some of it, I think, is our influence and the inspiration they got from us. And then we're looking at different modeling of different things, like ride-sharing, multimodal travel of users, real-time information choice. And you can, of course, think of all of these things under this disruptive conditions. So real everyday conditions are one thing, but we're also looking disruptive conditions. We are also, as I said, integrating different data sets, not only to do data analytics, but also to calibrate and validate these models. And this is one of the research areas of interest to me. So I'm going to show you a couple of fun slides. This is the taxi data from 2011. This data is still available from New York City. And by just plotting this data, you will see some anomalies. And this is what I mean by simple data analytics. And then you will see, then you can go back and find why these anomalies are happening. So August 28, 2011 was Hurricane Irene. December 25 was Christmas Day. So you can easily do that. And this is work done some of our friends in computer science. But you can also try to look at these, the way traffic, in this case, taxi demand changes, and then try to do like time series prediction. So we basically, as a response to COVID, we built this, what we call the COVID pandemic's data dashboard. So in this dashboard, first time operationally, we incorporated a number of data sets together, data sets that are publicly available and data sets that we generated ourselves. And this is available to everybody. So there's a link, you can go and check the data. So we incorporated data from transit ridership, speed travel, camera violations, vehicular volume, crashes. And also this social distancing data is an example of data that we generated. We used traffic cameras from New York City to grab the images and then convert those images into metrics that we can use for understanding pedestrian density, social distancing, and so on. And also, I told you before, the BQE, we installed weight motion sensors. So we are getting truck weights and so on. So these are two data sets that we collect and then we make available. So just going back to the social distancing, I don't know why this is going so fast. Social distancing data. So basically, New York City has around 700 cameras. We are recording 105 of these camera feeds and then saving that information. And then we're using deep learning-based video processing algorithms with the students who are not necessarily computer scientists, but who are interested in this. So this is off-the-shelf tools with some creative ideas to basically understand how we can process this data, not only to count vehicles and pedestrians, but also find the distance between pedestrians. So here there's some creative work. I'm not going to go into details of that, to approximately find how far the pedestrians are from each other. And that really helps with social distancing. And that now algorithm works in real time. So you can actually generate this kind of metrics in real time. So this is our framework. So we get data from cameras. We store the raw data. So one thing about this publicly available data streams, DOT they don't save them, but we save them. So it's like a perishable data. And then we use these deep learning algorithms for object detection and finding the social distancing patterns, and then convert them into things like heat maps, finding locations where there's too many people, it's too crowded, and we can do that for the whole city. So I've seen many NSF proposals. People said we're going to go out and count people or record them. Here, there is no direct contact. We can do all of that through traffic cameras. And in the bottom, there's a paper that we published recently. I put some, and also at the end of the presentation, there's some of these papers that we published, and you can go and read the details of this work. So this is actually how it looks like in the COVID dashboard. So basically, we grab the data in real time from the camera, and then we kind of convert, as I said, and then on the right side you see how the social distancing violations are changing. So you can use that as a regular citizen to see, oh, this intersection or this location is too crowded, maybe I don't want to go there. Or you can basically, the DOT can use that, right? We also built this, as I said, the MATSim New York City, very large agent-based model, not for COVID, just before COVID. So we are simulating 8.3 million people traveling within Manhattan. Again, there's a paper we published on that. This is very well calibrated. But when COVID started, we said, how can we use this? So of course, you cannot use it exactly what it was before, because travel demand changed. The frequencies of certain services changed. So basically, we went ahead and used the data that we collected, I showed you in the dashboard, to recalibrate this MATSim model for COVID conditions. And then we tested different scenarios and then see how travel times and then use of different modes are affected. Again, there's a recent paper that is coming up at Transportation Research Part A. So this was something interesting that we could do very fast. And actually, then you can use that moving forward to kind of understand the impact of COVID-19 on demand and transportation system. And actually, we're trying to convert that into emissions and how it affects the emissions, actually. Okay. So this is pretty much the summary of what I described. So we can, test different scenarios, and then you can test different ideas in terms of making people, move more comfortably or understand the impacts of, for example, not having a certain service 24/7 or frequency less than half of the frequency before COVID. So all that we can now test it very on a reliable basis, because we have the data that we were able to use to calibrate this model. And so this is kind of an example of, so on the left is pre-COVID, on the right is post-COVID, and then you see, of course, the network is less crowded, and then the hotspots changed, and then there's obviously a lot of post-processing with this data. And then below there's a paper that we published recently that talks about this work. Okay, so now, so this was the COVID thing. So going back to like a more traditional, like things like hurricanes. What do we do? How do we do that? How do you do the modeling? So I'm gonna, so most of you are familiar with different kind of hurricanes, and then many states work on that planning. Like, how do we plan for major hurricanes? In fact, although it's up north, New York City is prone to hurricanes. And then recently, Hurricane Sandy had a major impact on in New York State and actually New Jersey. So basically, we did a lot of work and many papers on this, understanding the impacts of Sandy, and also how to plan for that. So one of the, so you see these are all, so of course, United States is not the only place suffering from this kind of events. So there's a lot of these events that you need to kind of plan once the event happens. So the different parts of this evacuation planning, and I'm not going to go through every detail of that, but I'm going to touch on some of the issues that I think that are important. So for the transportation, there are three things that we really talk about. One is the evacuation demand. How do we basically determine the evacuation demand? What is the, and how does this affect your predictions? Then the capacity. Capacity is really important. So we're not in the same classroom, so I cannot ask you questions, but you know, most of these studies are done, planning studies, assuming some average capacity or best capacity, but that's not true. You know, when evacuation starts, you know, certain services are not functioning as before. There's also things that are happening before, for example, the hurricane makes a landfall. There is rain, there is high winds, so you lose some of this capacity. And how can you incorporate that into your evacuation planning? And then in the end, like what kind of models you need to use. So this is two examples of more recent hurricanes in Northeast. One is Irene, one is Sandy. As you see, they're relatively different, and they were also different in terms of their impact. For example, what happens is if it rains heavily before the hurricane, the high winds make a landfall, that has a different impact. Then a lot of trees are down and so on. But if it doesn't rain, and actually that's also local, certain places it rains a lot, certain places it doesn't, then the trees tend to stand and then they don't really reduce capacity. And also the path of the hurricane changes drastically every time. So this is the kind of framework that we used for a large project that we worked on. And again, we looked at the evacuation planning from a system level, from a more macro modeling level, and then micro level. So again, I'll talk about some of these here just to give you some ideas. Okay. So one research question that we had, can we use existing urban demand forecasting models that already exist and done in CUBE, Transcat, WISM for evacuation modeling? This question is important because you know, a lot of people, they want to build this dynamic models and simulation, but then that means for most of the MPOs, most of the cities, they have to have two types of models. One they use for their planning, and then one they have to use for evacuation and so on. And then it's costly, and most of the locations don't have those dynamic models. So what do we do that? You know, so this is the summary of some of the tools that we use in evacuation modeling. It goes back to 1980s, and actually, if you see here, MASVAC is and then TVAX and MASVAC 4. These are all came from researchers who worked at some point at Virginia Tech, where I did my PhD, and I was kind of familiar with some of these things, and that they were not all for hurricanes. Some of them were for evacuating a region, for example, if there's a danger of nuclear power plant and so on. And then most recently, there is some models, more dynamic models used like DynaSmart or DyNav for this purpose. So again, this is the question. Can we use the existing planning models for evacuation modeling? So pros obviously clear. You know, they exist. Agencies maintain and update those. They're in general very well calibrated. The data is already collected. The cons, they're static. They're time of day models, but evacuation actually is for the whole day, and they're deterministic. In the modeling framework, you need to really think about like what is the region, how do we create the demand tables, what kind of network adjustments you have to make, and how do you analyze the output? Because the output will be big, will be, for days and for every hour. So we actually tried to do something that has been done before, but kind of with some tweaking. So we wanted to use a quasi-dynamic approach. So I'm going to give you some idea about that, and then you can go back also read the papers. So basically, we modeled this NIMTEC region, the New York metropolitan area. This is a very large region. It's prone to hurricanes. We did the analysis at the traffic analysis zone level. And then we developed the demand matrices, and then the traffic assignment was done in Transcad, and then we tried different scenarios to understand the effect of different evacuation, impacts. So let me see. So there are different zones, some mandatory evacuation zones, some zones that voluntary evacuation zones, and some safe zones. But along the Long Island, for example, there are many zones that you have to evacuate, and this is a very highly populated area with a transportation network that's prone to get congested. Okay, and then we use this very famous S-curve to model the time-dependent evacuation modeling. So basically, in the beginning, so if in general, it's a 48-hour evacuation period. People start evacuating. So this is the cumulative evacuation numbers. And then during the night, end of the first day, they stop or slow down in evacuating, and then it really gets accelerated later on. So and then we kind of use that kind of approach to determine develop demand curves. So so this is a different kind of demand than your everyday demand. So there's some background traffic. People continue to do some transportation related activities, but there is also people who are trying to evacuate. So if I go back, actually, one of the main questions is that if this is New York, if they start evacuating, I don't know if I had a map here. If they start evacuating, where do they evacuate? Where do they go? Do they stay within New York City? Do they go upstate? Do they go to New Jersey? And that's one of the issues that we had to deal with. Okay, so we use this idea of incremental hourly assignment. So the idea is very simple. So we do the assignment every hour, but we know that due to the hyper congestion, they're not going to be able to clear their trips within that 60 minutes. So what we do is at the end of each 1 hour assignment, we find trips that cannot be finished in 1 hour, and then we add that to the next 1 hour OD matrix. This is a very aggregate and very kind of a big assumption, but this is the way you basically transfer certain number of trips that cannot be completed to the next hour, and then you keep doing that. Okay. All right. So this is basically, and we're using a system optimal assignment, and the reason for that, we want to find out the best case scenario. So, and then in user equilibrium, we assume cannot be used here because really they did not have enough time to learn and to adapt to this kind of situation. So we use the system optimal assignment. So the only trick here is that if you go to the next time period, there are some trips on each link that cannot be completed, and we keep them on that link for the next time period. Again, you need to go back and do some calibration, but that is the way to basically reduce capacity in a way to reflect the queuing and other hypercongestion effects. So then we run many scenarios, and then you will see that these graphs, they're about percentage change, from the base case in terms of travel times, and then different scenarios, they give you different results, and then you can see where the congestion is likely to occur. So I had a small. So basically, if I visualize the congestion level on the links over certain time period, you see it started congested and it's all green because it's night. People are not evacuating during the night, according to the S-curve. And then in the morning, they still start evacuating and there's some background traffic going on. And then you see that there is congestion and so on. And then we take all that information and we basically find like the hot spots and so on. Okay. So the second thing that we have done, and I think this is kind of a unique work, is to incorporate link failures into our model. So the question is, can we predict the new, so forget about this. So this has to come later on. So basically, link failures. Why do you have link failures? You have link failures because you have tree downs, you have accidents, you have cars that ran out of gas. You read some of these things. So can we really incorporate all these effects into our model to understand the effect of capacity loss on evacuation? So this is basically data that we received from New York State during Sandy, and again, it gives you different kind of failures like accidents, debris, downed trees, flooding, and others. I mean, flooding is a major issue on the seashore. So we actually have that information. So not only you have the frequency, but you also have the duration of these events. So some of them, they are cleared very quickly. Some of them cannot be cleared very quickly. So you need to have also that into your model. So we have estimated a simple negative binomial model for the frequency of different types of these events. So we generate them for different links. And there's some sophisticated decision making that goes into that. So for example, if the Monte Carlo generates two events that are too close to each other, we need to look at that a little bit too carefully. But we also do a model for the incident duration, as I said. So after you generate the incident, you also generate duration for that incident conditional to the type of the incident location, and occurrence time. And this is a log normal distribution. We assume that travel times or incident durations are log normal in their distribution. Now you can, if you have more data, you can use other machine learning methods and so on, but these are well-known models that we have estimated also in the past. So we are using same ideas, but different data. And now you can run the traffic simulation with links attached to these capacity reducing events. Okay. So basically, we generate the incidents, we generate the incident time, we generate the incident duration, we generate number of lanes blocked, we generate we look at the overlap incidents, so we don't allow too many overlaps, and then we incorporate that into our model, and then we run our model with incidents and without incidents. Of course, when you have this capacity reduction, then the travel times tend to go very high. For example, we know that for our model, the evacuation demand PM travel times are significantly higher than the AM travel time. So people, evacuate during the PM. But then during the first hours, 8 hours of the evacuation, when you have the capacity reduction, travel times increase drastically. And then for different scenarios, we see increase in travel times of 20 to 30% compared to the base case scenario when you have these capacity losses. So one of the things that we did to validate this, so we run the model without capacity loss, with capacity loss, and then we use the taxi data that I showed you in the beginning from the time of Sandy to calculate the actual link travel times using the taxi data. And then we compared the model travel times with the travel times that we observed travel times from the taxi data. And we saw that actually when you incorporated capacity losses, our travel times, model travel times became much closer to the actual travel times, because, and we knew that there were a lot of events like flooding, tree downs and so on. So we were able to capture those with our approach, right? Okay, so basically, this is if you take something away from this, it's not always the best idea to do the evacuation modeling using ideal capacities. You have to understand that there will be capacities, full or partial, during evacuation, and you need to take that into account. Of course, it's very network topology dependent. So if you have a network like Florida, and there's one main big freeway going from south of Florida to the north, and then there's a couple of accidents, that might have much bigger impacts than a bigger network with redundancy, for example. But still, you need to really do your modeling with the understanding that you need to incorporate capacity losses. And now we have more data from all these different, hurricane evacuation events. So states can do that. It's not very difficult, but it has to be done, and it has to be taken into account. And that also adds the stochastic aspect of these evacuations beyond demand. So for the demand, we have some stochasticity. So we try different demand levels, but here you also have to look at the supply. And then this is how you incorporate stochasticity into the supply. Okay, so the third thing that I want to talk about is that the future of evacuation zones. So evacuation zones are important because people evacuate, they are asked to evacuate from these mandatory zones, and voluntary zones are also encouraged to evacuate. And the states, they identify these evacuation zones once every decade or maybe more than that. So how can we make sure that these are the correct zones? Are they really covering everything so that we don't put people in jeopardy? And then the main question here we focus is that what happens to these evacuation zones after the sea level change? And this is actually joint work we did with SUNY Stony Brook. So they have a big climate model. So they ran their model to give us the predicted sea level change for a hurricane that's similar to Sandy. So when there's a hurricane, there's a sea level increase no matter what, but they added on top of it the expected sea level change as a result of global warming. So basically, we wanted to learn the relationship between current predetermined evacuation zones and hurricane-related factors, and then use those to upgrade or modify the evacuation zones in the future when there is a major sea level change. Okay, so this is kind of summary. So New York actually has a lot of coastline, and then they were affected by Sandy and Irene. So the idea here was to create a grid network, street by street resolution, and then attach them this different type of evacuation zone IDs, and then find the features that define these zones, like their elevation levels, the historical hurricane information, and so on. So we had to bring all this data together to kind of build a model that will allow us to predict these evacuation zones that are predetermined by the state. So we assume that what the state has is correct, but we're trying to find the features that make these locations one or the other type of evacuation zone. Okay. And then we have a descriptive analysis. Basically, we looked at the elevation from the sea level, distance to the coast, as a result of the hurricane, what is the building damage intensity, the nearest distance to the evacuation center, and then other factors in terms of mobility, we also added them. So we wanted to find what are the features that define these zones, and also we added the demographic features. And for demographic features, the total population was the main thing that we considered, but we also looked at the age, distribution of the population. Okay, so we add now all this information, and then we try to find the relationship between evacuation zone categories and hurricane-related factors, also some of the inherent factors. And then we used a decision tree type of classification. This is quite simple. So we try to find what are the variables that define these zones. We also used random forest. I mean, this is a machine learning technique, very simple. So you basically build this decision trees, and then use a training set to develop these trees, and then see if they can predict, their average can predict the types of zones as an accurate classifier. So I'm going to pass this. So basically, we compared the simple decision tree idea with the random forest idea. I mean, there is some difference in accuracies, but you can use either one of them. And here the data set is not huge. So, so random forest is computationally a little bit more expensive, but it has around 4% improvement in terms of accuracy of prediction of zones given the different characteristics. So you can use the random forest approach. If you're dealing with a much larger state or smaller zonal descriptions, then obviously you have to consider the computational aspects of it too. Okay, then what we did is we looked at the climate change and sea level rise as a result of climate change, and then added only that factor is a difference into these zones, like assuming everything else remains the same, and then we use the random forest model to project evacuation zones in the future based on the climate change. And then what we found out that actually so if we look at 2050 and 2090, there are many more cells that are now qualifies as evacuation zones. So basically, if you had obviously this is only one scenario for one hurricane. So you need to do this for different types of hurricanes. As I said, hurricanes are different in terms of the path, the way they do the landing, and so on. So this is only for Sandy type of hurricane because their model has to use that. So this can be a very time-consuming and computationally expensive exercise if you have to consider different types of hurricanes and then see what they do. We haven't done that. That needs a major investment, but this was just a proof of concept. And then we saw that even with this one hurricane, in the future, there might be a need to change the evacuation zones. And this is what our model predicted. Okay, so let me just, I have a few more minutes. So basically, there are many important questions. Decision of timing and time of mandatory evacuation order, when to do that, again, depends on the hurricane, depends on the network topology, the number of people who need to be evacuated. How do we model the evacuation compliance? Not very easy to do. So we assume certain numbers of percentage of compliance, but that's a main topic. How do you manage evacuation routes? What happens when there's a partial loss of evacuation network? So we only work with one data set, but you need to do a better work. How do you model HOV and bus evacuation in areas where people depend on mass transit? And then what is the real-time management of emergency management operations. How do you do that? How do you manage them in real time? And finally, I don't have time to talk about this. These are all kind of, when there's a problem, you deal with that problem given what you have. But the main question in my mind should be how to build more accessible and sustainable cities that can allow us to deal with this kind of emergencies like hurricanes, pandemics, earthquakes more efficiently. So I'm not going to talk about, I'm looking at my watch, it's like 48 minutes. There's some slides, but those are important questions. So our future work that's going on right now, we develop regional agent-based evacuation models with stochastic demand generation. We're looking at again, the spatial models of resilience with crowdsourcing and other relevant ubiquitous data. This is a NSF project that part of the project that generates that kind of data. We are now looking at cascading failures. And this is just a one sentence. This is important. No? For example, if the power network fails, then all traffic lights fail. And in a city like New York City, when there's 10,000 traffic signals, that's a problem. So how do you deal with that? How do you have resiliency to deal with this kind of problem when one failure creates another failure? And then when the signals fail, you lose capacity, but you might also have additional accidents because you lose traffic control. And then we think that the last bullet, you need to collaborate more with climate change and other researchers to model this kind of issues that I just mentioned briefly. And then here, these are some of the papers that are related to this work. I think I put some of them in red. I didn't have time to talk about them. The first one, we looked at, used the machine learning methods to look at the COVID-19 policies and their lagged effects, like how fast they were adopted by people in New York City and Seattle. The second red is, we modeled how to leverage right sourcing services in hurricane evacuation, because many cities now depend on right sourcing services like Lyft and Uber, and what's the best way to understand the effect of these. And then we looked also at the simulation and modeling of cascading failures during hurricane evacuations. This is also some preliminary work, but there's much more to be done in that area. So with that, I'm going to be quiet and then see if there are any questions.
Well, thank you, Kaan. That's certainly a lot of materials to digest. So now we go to the Q&A part of the seminar. Again, I will use your raise hand feature to ask your question, and then we'll start with our student audience first. And once we have the students ask the questions, and then we open to the outside audience. And for our outside audience, we use the Q&A feature to ask your question. Okay, from our students, any questions? Please raise your hand. Well, let the students maybe take some time to kind of digest the materials. And I have some questions that Kaan, I would like to kind of sum up.
Michael, I'm losing you. I think you're breaking up.
Clarification questions for the pedestrian. Can you hear me now?
Yeah, I can.
Okay. So for the social distancing part, for the pedestrians, so you basically use the data from the city, collected by the city, the raw video data that kind of stream to your lab or to your center.
Yeah, this is publicly available data. So they stream this data. So basically, we grab that data from their web page. They don't save that, so we just save it, the frames. Oh, and it's a low frequency data and low quality data. So, I mean, there's also IRB. We shared it with the university, so there's no privacy because we don't see the faces, we don't see the license plates. But this is data that is on the public feed from the traffic cameras. We are just, and we call it perishable data because it gets lost if you don't save them. So during that time period, last 6-8 months, we saved it. So it's some gigabytes of data, and then we process that.
Mm-hmm. And do you happen to use like a software like a ULO, or you develop your own?
Yeah, no, we used. You're right. We used ULO with some filters that we developed our own. So basically, you have to make some kind of an approximation. So we assume every person in that frame is in a box, like a predetermined box. So it's like a area of interest. So we assume that every person is the same height. So because of the distance, that works well. So the height difference doesn't make a difference. And then we find the middle point of each box and then calculate the difference between the middle point of boxes. So that part is ours. So there's some nice algorithm that we use to do that. This way we can have an approximate difference calculation between the pedestrians. Now, one way to make this more accurate, you have to send someone to the field, and then they have to have a post or something of like a known height. In traffic, we do that to calibrate because there's a perspective problem based on the location of the camera and so on. But in this case, we don't have to do that because we are, again, approximating everything, and that works fine. So what we did is we did a couple of cases where we did this kind of measurements to validate, and we saw to our happiness, whatever, we were very happy to see that the results are pretty good. And actually, the higher you are, so I did similar kind of thing from 19th floor in my office, then the better it becomes because every object becomes very small from that height. So you don't have to really care about the perspective or small dimensional differences. So in that sense, traffic cameras are okay. If you can go high up, like if you have a drone, for example, actually it's even easier. So more difficult to collect data from high up, but once you have that data, doing the image processing becomes very almost trivial, much easier.
And New York City is certainly one of the places to have collect data for multimodal transportation.
Definitely.
We have a kind of a unique advantage of that. I remember a couple of years back, there's this pilot test study for connected autonomous vehicles. One of the places to do this pilot was New York City. Do you guys have access to their data as well, or
yes. I mean, we are, that data is, so we are their university partner with City University. So we work with them. So we are doing the safety evaluation. So there are a number of apps, safety apps. So we are working with them to do that. And I didn't have time to talk about it. We do the safety evaluation based on the app warnings. And the data is still not publicly available. I mean, they keep the data internal, but we are also working with them on a pedestrian application for visually impaired pedestrians. So basically, if a visually impaired pedestrian has to cross an intersection, how do you do that? So there's an app that's being developed, and we will evaluate that. So definitely we are part of that testbed, and we are now, I mean, after many years of work, seeing the data coming in, mainly the event data, like warnings and so on, but still it's in testing and it's not publicly available. Hopefully in a short period of time, it'll be more, we'll see more data.
So, I mean, clearly, the future is for transportation studies, whether it's, like COVID or hurricanes or the, conventional studies about ride sharing or bus transit. data it's a critical part, and it will be a lot more data driven. And from your talk, we can see that there are so many different kind of data, and they have different owners and different accuracy, and also different sort of the strengths attached, whether how you can use it. So from your you definitely have a lot of experience dealing with this. From your perspective, how is this sort of a data-driven approach is going to take shape, like how the future looks like, and will we get rid of the models and just purely based on the data and machine learning and so forth, or we'll still have to to look at the data ourselves and analyze it and maybe combine with the machine learning and other approaches?
I mean, great question. I mean, there are a few things. For the things that I discussed, like emergency evacuation, data is still limited because these are rare events. So you don't have much data for emergency evacuation and so on. And COVID was an anomaly. So we had a lot of data during COVID, but other things, the data is not available. Of course, for every day, now there's more data available, and actually more data than probably you can deal with. There's a lot of data, but most of that data is not in clean format, and it's not even saved. So you need to go find the data, and also using one set of data is not always enough. So you need to combine different data sets. So this is what we're trying to do. The whole is bigger than the pieces. So that's one thing that we need to do. We need to know how to incorporate different data sets together and make sense out of them. And that's very difficult. Now, there are a lot of companies who are trying to do that. I shouldn't say a lot of, but several companies. But they are, there to make money. So you don't know how they're doing it. You don't know their algorithm. You don't know, that's your expertise too, Michael. Sometimes, from a traffic engineer, that data, the way they're doing it doesn't make any sense because they get rid of certain data points, for example, thinking these are outliers. But that's a shock wave, so that it's just a congestion. But, I think we have to be careful, when dealing with commercial data. And I think the data should be open data, open. That's why we use MATSim and Sumo for modeling, because they're open. So I think, one thing I can say, the data also should be open, and we should work with agencies to make the data open and as disaggregated as possible. Because when you aggregate the data, you lose a lot of the information. But that's the future. And now, I see, for example, a lot of people using drones to get trajectory data and so on. And that's great. I think they should make more of that data available to researchers and to agencies. But we still have a long way to go to make it open and easily accessible. Still a problem, but definitely we have more data than 20 years ago. That's for sure.
Yeah. And Kaan, you have a unique vantage point of dealing with all this different type of data and look at these different applications of the data. For our students, to prepare them better for the future in terms of this kind of the data-driven world. What do you think? What are your suggestions for them in terms of the knowledge base that they should build, like type of courses or training they should have, and maybe you can share your thoughts on this.
My background is operations research mainly, so I'm not a statistician, but I think learning statistics beyond the level that we teach in civil engineering is very important, because you need to be able to analyze this data. So, and also dealing with this data. So you need to know how to do data analytics, how to, so good programming would be very important. But most important, I think so my students now, I make them take, graduate students, at least 2 advanced statistics courses, because it's really everything is based on that, so, and the other thing, of course, they have to be very comfortable with data acquisition, data processing, so they need to take a couple of courses. So I teach this course called Data-Driven Traffic Simulation and Modeling. And like I think the second assignment is so I teach R, our language, like in R, and a couple of students, they always come to me, they say, can we use Excel? We don't want to use R, okay? I say, yeah, if you can, fine. But then there is 1 million rows and then 1 million columns, so you cannot use Excel very easily with that, you can't even scroll down, up and down. So then they come to me and they say, okay, Excel doesn't work, so let's learn R. So we teach them R. So learning R or Python is really key. And I mean, I learned R on my own like 10 years ago, when I was teaching this class, I said, okay, I need to add this component. I think students can do 10 times better than I can. They're young and smarter and faster. So what they should definitely focus on those.
Yeah, we have a graduate level class in our program in the TTP and civil teaching data analysis using R.
Yeah.
I don't know whether it's using Python or not, but definitely learning.
Yeah, R is very good, I mean, it's not good for every kind of programming, but for this data-driven programming is really good. I mean, the other thing I can say, when they do machine learning in other departments like computer science and so on, it's mainly, I mean, if it's like introductory course, black box, but our applications are very specific. So they need to learn really, they need to have an idea how that black box works, if they don't do that, they'll end up getting some, so in simulation, we call that, junk in, junk out, so you get some results, so machine learning is exactly the same way. You might get some results that are numbers, but they might not make any sense. So learning the basics of machine learning, which is very hot nowadays, is very important. So they should try to learn that too, the basics of it. I mean, and everything else changes too quickly, if I can give an example, there's a very nice research. I listened to the presentation. So one of the computer science professors, she used 5 different clustering algorithms, k-means type of algorithm, with the same data set. And they got 5 different results in terms of computation time, in terms of clusters they generate. So their conclusion was that every paper uses the best data set for their own algorithm. But this doesn't mean that it will work the same in every algorithm. So they have to be really at least cognizant of that. So, and understand what's in the black box, at least conceptually, Yeah.
So we have a student, question from a student, Maha, you can ask your question.
Thank you. Hi, Kaan. Thank you for a very interesting talk. And I really appreciate your advice about R. We actually, as Michael said, take a couple of courses on that. So we are pretty familiar with it. Would you mind telling us a bit about MATSim and like your experience using that? It's a less popular software, so I don't think we have courses on it. Mm-hmm. But yeah, is that self-taught as well? What's your experience using
so
that?
Yeah, it has a relatively steep learning curve. It's not very easy to use. But what we have done, we have open, we call it like a learning hub. And I can send Michael the link, the center. So we have like an introductory lectures that we recorded and made available. So if you guys want to take a look at it, you're welcome. It's free for everyone. But I mean, it's not very difficult, but just to get it like a first shot at it, it takes time, once you do that, it's not that difficult. I mean, it's not difficult than other software packages. The problem, so the advantages and disadvantages. The disadvantage is that it's not commercial, so you don't get commercial support. So when you buy VisSim or AIMSON, whatever, you get commercial support. This one, you don't. But because it's open source, there's a huge community. So people post a lot of new algorithms, new ways of simulating. So there's a lot of new things to do, and then you can add your own algorithms. But it's, I mean, probably first 1 month will be painful, but after a month, I think that's fine. You'll be able to run it. The other thing, if your network is too big, you need a powerful computer. I mean, it's computationally expensive. Same is true for Sumo. Sumo is a great traffic simulation. I mean, very versatile, but the first 1 or 2 months of learning it is not that easy. After that, it's just very flexible, very nice.
So Maha, if you want to know more about MATSim or Sumo, we have people in ITS like Caroline Rodier and Professor Miguel Taylor, and some of their students are using the MATSim software, and they actually developed models for the San Francisco Bay Area.
Yeah.
Using MATSim, and I myself and some of the students using Sumo to develop simulation for the city of San Francisco and some other small networks.
Yeah, I mean, all my career, I used Paramix, for example, but recently we stopped. Recently, I would say 5, 6 years ago, we stopped doing that because Sumo is so much more powerful and open source, you know. So, but definitely, I mean, I can send Michael the links. So that's one of our initiatives. We call it like a student learning hub. So we want students to give like introductory lectures on using these software packages, and you can watch them. It's like a 40 minute, 1 hour. I think they're useful.
That'd be great. Yeah. Any
Thank you.
Any other questions from our students?
I think I confuse them a lot, so they're being quiet. They just don't want to ask anything.
I think it's just a lot of materials in the talk, so people probably takes time to
digest it. Yeah, definitely.
Digest
but if you watch the presentation again, if you have patience or parts of it, please feel free to email me. I'll be glad to write back to you. Yeah. So the presentation is recorded and it's uploaded in our course website, and also it's on our ITS, I think, YouTube channel. But the exam question will be from my bio. I'm kidding. We have that as well. They can have my short version or have your longer version. Any other questions? Okay, if not, and we want to thank our speaker, Professor Kaan Ozbay, again. And a round of applause, and then I think we're almost getting 3 o'clock, and so we'll stop here. And thank you for tuning in, and wish everybody have a nice weekend. Thank you, everyone. Thank you.
Thank you.
Bye-bye.